Okay, we're live.
Let's double check the thing.
Yeah.
Not allowed.
It doesn't say we're live.
We're waiting for GPU mode.
Alex, can you hear us?
Yes, I can. I think it is.
No, we're
Yes.
good.
Okay.
Yeah.
Okay. Okay, so we can start. All right, so we have Songlin here with us today. So I will have the honor to do Songlin's intro. Songlin is a now third-year PhD student. You got to update your website. At MIT CSAIL, advised by Yoon. She earned her bachelor's degree from SUS Tech in 2020 and her master's degree from Shanghai Tech in 2023. Her research focuses on the intersection of machine learning systems and large language models with a particular interest in hardware-aware algorithm design for efficient sequence modeling, especially in linear attention models. And she's a strong advocate for open source research, and you can see her work as Flash Linear Attention, and the best way to reach her is through the FLA Discord community. So take it away, Songlin.
Okay, thank you for the intro. Hi everyone. Today's talk is titled "Modern Positional Encoding in Transformers," and I'll be mainly talking about rope, yarn, and another work, PaTH. So first, we have our motivation for the positional encoding. When the transformers was invented, they were used for bidirectional modeling and self-attention mechanism without the causal mask. Treats the input token as an unordered set. So if you do not have any positional embedding, and the transformer attention mechanism would act like a bag of word model. It does not have the sense of the word ordering. So this is why we want to have positional embedding in the first place. Here we have a very intuitive example. We have two sentences, and the cat sat on the mat, and the mat sat on the cat. And if we do not have the positional embedding, the model cannot distinguish between the two. When we do not have the causal mask, and this is a precondition. In the original transformer paper, they add a very simple absolute positional encoding. So basically, they have this cosine and the sine function as the absolute positional encoding, and these functions are is a periodic function, so they can encode certain positional information. And then later, researchers realized that absolute position encoding is not that perfect. It has a lot of limitation. For example, the content is highly coupled with the absolute positions. So it does not directly model the absolute, the relative position between words. It learns some kind of like correlation between the word and the position, which we do not want that. So later on, researchers are mainly focusing on relative position encoding. And today, we'll be mainly focusing on the rotary positional embedding, which is the most popular relative positional encoding scheme. Here we have an overview of the rotary positional embedding. So first off, we have the input embedding, and for rope, it divides the input channels into different pairs of channels. Each pair has two dimensions, and for each channel, rope has a frequency angle, and it takes the absolute position ID to here, and here we have the angle. And we do this rotation based on both the angle and the absolute position ID. Later, we'll show this is indeed a relative position encoding. And despite that, here we use this absolute position ID to calculate this rotation. And after this rotation, we obtain the rotated queries and the rotated keys, and we put it back for calculating the attention logic score. We do this operation separately for different pairs of channels. So here we have another, for this 2-dimension colored in pink, we have another rotation angle, and we have a different rotation based on this angle. And the different channels pairs act independently. They do not have interaction to each other. Before understanding the rope mechanism, first we have a brief recap of the rotation matrix. Here we have a 2-dimensional rotation matrix. And this is very simple. So if you want to rotate a vector by theta angle, you can use this 2-dimensional matrix to achieve it. And this rotation matrix has a lot of very good property. First off, it has the power property. Basically, when you do this cumulative product of this rotation matrix, you do not need to actually calculate the cumulative product one by one. You can directly calculate the resulting accumulated angle and only calculate this matrix once. Second, because the rotation matrix is an orthogonal transform, so the inverse of that matrix is equivalent to the transpose of that matrix. And also, we can use the negative angle to do this inversion operation. So imagine if you if a vector in the 2-dimensional plane rotate a theta angle in this direction, and you only need to rotate it back using in the reverse direction. And here the milestone indicates the reverse direction. Finally, if you want to do the composition of multiple rotation matrices, it's also very simple algebra. You only need to sum up those rotation angle, and you use the resulting rotation angle to do the final calculation. For rope, as we mentioned before, it operates on pairs of dimensions independently. So we have, if the input dimension is d, then we have d divided by 2 number of channel pairs. And for each channel pairs, we have a different rotation angle. And in total, we can write this in a block diagonal matrix form. So block diagonal means, okay, this part are basically independent to each other. They do not have interaction. Different channel pairs do not have interactions with each other. They do the rotation in an independent manner. And this block diagonal matrix also preserve the previously mentioned property, the rotation properties. And then we have this basic knowledge about the rotation matrix, and then we can have a matrix form to write down the rope working mechanism. So here we use this as an abbreviation for this. And then we for each position, we take the absolute position ID. For example, in the S position, we use this I as the exponent to do this matrix exponent of the rotation matrix. This looks like the absolute positional encoding scheme, but here we are going to show that this absolute encoding scheme actually it encodes a relative position information. And so when we take this dot product between the transferred query and the keys, we have these two terms, and we can this transpose equals to the matrix inverse, right? So we can imagine here we have minus I in the exponent, and we compose these two together. So we have this we have this angle difference, and
Like
this
the relative angle.
the relative angle.
Yeah.
So it's basically so here we can easily see that this is totally depend on the relative difference and position difference between the query position and the key position. Yeah, although here we use this absolute encoding scheme and to obtain the rotated vectors. By taking the dot product, we eventually have this relative position encoding. And this is a very interesting property of rope. And so you can do some very simple absolute position-based transformation, and then you can directly use this dot product to encode this relative position. It is very cheap. And this property is also very less, and it has been used in many open source models like Llama, Queen, etc. Previously, we mentioned for different channel pairs, they have different rotation angle. And so based on their theta's value, we can categorize them into two different categories. The first one is those high frequency channels. So they have very large theta value. And these channels do the rotation in a very rapid manner. And for these channels, there is a very interesting paper called Round and Round We Go, what makes rotary positional encodings useful. This paper is really well written. I learned a lot of insights from this paper, highly recommended. And in this paper, they discuss the different functionality between different channels. So for these high frequency channels, it was mostly used for encoding the positional patterns. For example, if you want to find the case nearest word, it relies on these high frequency channels to achieve it. And more importantly, NOP, which is another positional encoding scheme, because in autoregressive modeling, the causal mask itself could be imagined as injecting some positional information. So recently, there is a significant interest in using NOP for positional encoding. And this paper showed that for NOP, it doesn't have such mechanism to to find these positional patterns. On the other hand, for those low frequency channels, those has very small rotation angles. It do the rotation in a very slow manner. So these channels are mostly used for encoding the semantic meanings. And because the rotation is too slow, it has minimal impact on the resulting dot product value. So in this sense, the dot product attention logic value is mostly based on the similarity between the queries and the keys. So in this way, it could encode more semantic information. For high frequency channels, because it rotates so fast and the dot product could change rapidly, so it was mostly used for encoding the positional patterns. So as such, we can see this division allows rope to effectively balance positional and semantic information. Okay, rope is a very nice relative position scheme, but it still has its limitation. For example, the first issue is the less in the length extrapolation. So basically, for example, when the training sequence length is 4K, and if we train on 4K sequence length, and then if we evaluate the complexity beyond this training sequence length, and then the complexity would blow up in a very rapid manner, and eventually will blow up to a very significant large value. And in this sense, this is a common, a well-known problem for rope. It cannot do the length extrapolation very well. And the researchers have developed a lot of workaround for improving the length extrapolation of rope. For example, in this earliest work called positional interpolation, basically it does the scaling for the rotation angle to make sure the product between the absolute position ID and this rotation angle is still this resulting values has been seen during the training, so it does not have the so-called out of distribution issue. However, this positional interpolation scheme is too simple. It uniformly adjusts the rotation angle for different channels without distinguishing different channels. So as we mentioned, for those very high frequency channels, we'd better not modify that rotation angles because it rotates really fast, and when it comes to the training sequence length, that channel must be rotating for multiple cycles, and there's no out of distribution issue here.
Songlin, we have two questions. So the first question is, why does the perplexity of the model shoot once reaching the 4K plus context window?
Yeah, I think there are a lot of explanation for it. For example, a commonly believed explanation is that for some certain rotation channels, because it rotates very slowly, and the model doesn't see the rotated angle during pre-training. Yeah, and when we do this length extrapolation, it will have some out of distribution rotated angle, and the model doesn't know how to deal with it. And this is a most common explanation for it.
But then but when you do attention, you're taking the dot product, everything gets converted into relative angles, right? But that's something that the model probably would have saw.
Yeah, so you need to, based on the channel's rotation angle, to decide how to scale that rotation angle. Yeah, for some channels, if it
Okay, so
rotates.
you're saying that the relative gap can also start to increase.
Yeah.
Okay.
Yeah, I'll explain it later.
Okay. And then we have one more question, which is Dean asks, does this mean we are conditioning initial embedding dimensions to capture position, but later ones to capture semantics? Why would this bias towards initial dimensions for positional?
Sorry, say that again.
Does this mean we are conditioning the initial dimensions of your embedding to capture the position, but then the later ones to capture semantics? This is related to the high frequency, low frequency part that you just like touched upon.
Yeah, so why would this bias towards initial dimensions for position here? So yeah, I think these initial dimensions is corresponding to those high frequency channels, and it does the rotation in a very rapid manner, and as such, the rotated queries and rotated keys could be changed significantly, and the semantic information doesn't really that matter there because the dot product could be changing significantly. So in this domain, the dot product is mainly dominated by this rotated angle. Yeah, and since it only depends on the relative position, and for these channels, it could be a very good chance to use them to encode this relative position only. And for those low frequency channels, because the rotation does not have much impact on the resulting dot product, so they are used for encoding semantics. Yeah, in positional encoding, we definitely want to encode both the positional information and the semantic information. And the rotary position embedding scheme provides such a divide of work into different channels.
Nice. Okay. I think that's all we have for questions now.
Okay, personally, we show that, okay, this position interpolation scheme evenly address the rotation angle for different channels, but it doesn't take into consideration the sensitivity of different rotation channels. So later, there is a NTK-aware rope angle scaling scheme. So in NTK is short for neural tangent kernel. In this theory, it shows that the deep neural network struggles to learn high frequency information when the input dimension is low, and the corresponding embedding like high frequency components. And this is exactly the case for positional encoding, right? The position ID is just a number. It is one dimension, and we use a high dimensional vector to encode this positional information. And then this theory, this conclusion could also be applied to rotary positional embedding. And in the NTK-aware interpolation, since high frequency channels are more sensitive and it's more fragile because it is more difficult to learn in a neural network, and then we do not want to break down this learned frequency because they are very difficult to learn and they are really fragile, and we want to keep them as it is. So we do not change the rotation angle for those very high frequency channels. They are purely doing extrapolation. But for low frequency channel, we can do this interpolation easily because they are low frequency channel. The rotation has minimal impact anyway, right? We mentioned those low frequency channels are mostly encoded for semantic information because the rotation angle does not change that much. And then we want to have a so this is inductive bias. We want these high frequency channels to keep the same, and we want these low frequency channels to do the full interpolation. And then we have these 2 points we want to satisfy, and we want to use a function to fit these 2 points. And in NTK, they use an exponential function to fit this curve, and you can input your channel's ID, and it will output the scaling factor for that rotation angle, and you use this scaling factor to multiply to your rotation angle. Then we have the resulting rotation angles for this NTK adjusted rope. Yeah, here is the key intuition. So these high frequency channels encode the fine-grained local order like n-gram and local syntax. If we scale this rotation angle, it will definitely distort this component and it will hurt the short range, short context accuracy. And the intuition is that we want to keep these high frequency channels unchanged. And for this low frequency channel, I think previously we have a question why the popularity will blow up. And here is the explanation because by up to the training sequence, the model this rotation channel only rotates like half of the entire cycle, so it doesn't know how to fit this the remaining part in this -9. So the model doesn't know how to deal with them. This is the so-called out of distribution issue with these low frequency channels. And in this case, we want to do the full interpolation to make sure that the rotated angles are within the range of the training sequence length. NTK is a smooth. They use the previous NTK use a smooth function to calculate the scaling factors of rope. But as we show, for many high frequency channels, we do not want them to be changed, and for many low frequency channels, we want them to fully do this interpolation. We do not want them to do any extrapolation. And the NTK by parts is a NTK variant. It is not using a smooth function to fit that curve, and instead it uses a stepwise function to fit that curve. So for some region, this one equals to 0, and for some, this equals to 1. And for the remaining one, it do the linear interpolation between the two. So for those channels in the middle, they both do the extrapolation and they also do the interpolation. For a very high frequency channel, they only do the extrapolation, and for very low frequency channel, they only do the interpolation. And here we have some function to calculate the resulting rotated angle. And the high-level idea is explained before. And the yarn position encoding scheme, and the forename of yarn is yet another rope extension. So the yarn is basically combining this NTK by parts with a temperature scaling T. So they have an additional term, this temperature term, based on the ratio of the new sequence length and the old training sequence length. And they calculate this temperature in this way, and they do not have much explanation in their paper. But I think this Jennings Su's blog post is very useful. In this blog post, he provides a lot of insights based on this entropy invariance of this attention logic score. And if you are interested in understanding the intuition behind this temperature scaling, you can check out this blog post. And also, Jennings Su is also the inventor of the rotary positional encoding embedding.
So Songlin, so stepping back a bit, in the initial plot you gave of the perplexity over length, we see that yarn does much better than rope, right?
Mm.
So just like what is like if someone didn't follow all of your like the technical details right now, what is like the core intuition of why the NTK by parts allows or enables for better length extrapolation?
Yeah, I can have some intuitive explanation. So you can imagine rope is like a ruler to measure the length, and the maximum measurement is like the training sequence length. And when we test on longer sequence, basically the ruler is not longer enough to measure the actual length. So we want to define some different mechanism to use that ruler to measure longer sequence length. And in rope, because it's not uniform, it's not uniform. It's not uniform measure. So for some channels, they are very sensitive, and we'd better keep them fixed, like those high frequency channel, because they change very rapidly.
Yep.
If you tweak that rotation angle, it will cause a lot of information loss. You can imagine those high frequency channel as the resolution. You'd better keep those resolution very high. You don't want to like lower down the resolution. And for low frequency channels, they are like a low resolution, and you can do some more more tweak on the rotation angle and the resulting, and it will not impact have much impact.
Yeah.
Okay, and so we know that for many recent open source model like DeepSeek, like Llama 4, and also the GPT-OSS, they all use as the positional encoding scheme. Yeah, and for length extension, they change the rope to using this to adjust the rotation angle, and they train the model on longer sequence to better fit the long the very long sequence. And this technique is very classical. And hopefully, I gave enough intuition for you to understand what's going on in this technique. Yeah, and in the second part, I'll introduce another work called PaTH. We argue that apart from the Nancy interpolation problem, those transformers also have a very fundamental expressivity limitation. So first we have two complexity hierarchy. The first one is the TC0, and the second one is NC1. I'll explain what are they later. So for this figure is drawn from William Miller's paper, The Illusion of State in State-Space Model. This is also a very classical paper. And in that paper, they show state-space models like member and transformers are all within the class of TC0. So they are not expressive enough to deal with those more complicated tasks like playing the chess, like do the coding or doing the state tracking. Yeah, because these models do not have enough expressive power to tackle down this task. And I think there are also some work showing that the train of thought could theoretically improve the expressivity of transformers. So this is why we need a train of thought and often very long train of thought starting by DeepSeek R1 to do more complicated reasoning tasks. And this is totally because the backbone, our backbone model, the transformer, has a very limited expressivity. And we have a brief overview of what is the TC0 class and the NC1 class. So for TC0 class, it has a lot of circuits, and the circuit is constant in depth and the polynomial in size. And we allow unbounded function for this AND, OR, and NOT gate. And we also allow for threshold gates. You can imagine it as a majority voting. The key intuition is that for some very shallow circuits, it can perform counting. And this TC0, many tasks of interest are within the class of TC0, like addition, comparison, prefix sum, parity tracking, and also even this integer multiplication and division. So these basic mathematical operations are mostly within the class of TC0. For the NC1 complexity class, it has logarithmic depth in terms the logarithmic in terms of the input length n. and we have polynomial size of the gate. And in this case, we only allow for bounded fixed amount of firing for this AND OR and the NOT gate. And the key intuition of this NC1 class is that it captures the parallel divide and conquer nature inherently. So this complexity class is very suitable for doing like for formula evaluation, like this Boolean formula evaluation problem is within the class of NC1. And also it can do some certain permutation composition, state tracking, and this more complicated task than the basic arithmetic operation.
Songlin, we have a question. So I think the first one's not. Okay, we have one question. So since rope only applies to queries and keys, does this mean no absolute position information can be propagated through the values?
I'll go back to the previous slides. And so here we have this absolute positional encoding like scheme to do this rope transformation. But here we have some math. We show that even though here we do this absolute positional encoding, and then when we take this dot product, it is act like a relative position encoding. This is due to some mathematical property from the rotation matrix I mentioned before. Yeah, here we have this rotation matrix property. And if we do this math, we have found even here we do this absolute position encoding, and it actually encodes, it just encodes the relative position. And then since we do not apply any rotary embedding on the value, so since the attention score is only based on relative position, then the resulting value shouldn't have any absolute positional information.
Okay, I think that's good for questions, yeah. We can go back to NC1.
Yeah, here we have the brief overview of what is TC0 and what is NC1. These are from the complexity theory. And the next we'll be introducing a very simple and a very minimal NC1 complete problem. It's a 5-element permutation. So here we have 5 elements, and we want to use a lot of permutation, and we want to apply permutation on this element, and we want to do a series of composition of this permutation, and we want to know what is the resulting permutation when we apply a lot of permutation. This is a NC1 complete problem, and since each permutation could be decomposed into multiple swap operation, and then we are focusing on the swap operation, and they are equivalent in terms of expressivity, because for each permutation we can use several swap to represent it. And if and then in the following we'll be focusing on this cumulative composition of swap problem. We have multiple swap. Each swap is swapped only 2 elements. It is not doing a full permutation. And this problem is exactly the permutation composition in the word problem called S5. Yeah, it's a NC1 complete problem. Yeah, we want to here we have our starting configuration, and we want to apply this swiping operation. We want to apply a lot of this swipe operation, and we want to know what is the resulting configuration. Yeah, here is the problem setup. And first, we also want to build some intuition why rotary positional embedding cannot do this task. And so first off, we can list several properties needed for this task. First one, this task is data dependent because like a swap the element A and element the position A and position B doesn't equal to swap two different position, right? It is a data dependent operation. And the second, and very importantly, this composition of swap is non-commutative. You can have a minimal example. If we do this swap A and position B, and we swap this B and C, then A will end up as C. But if we change this order of this swapping, and then it will obtain a different resulting configuration. But when we look back to this rotary positional encoding, so first off, it only have this position only rotations. It doesn't depend on the input data, and for each position, it rotates the same angle regardless the position the content in that position. So it's data independent. And the second, more importantly, because in rotary position encode embedding, they use the block diagonal rotation matrix, and each block size is equals to 2. And for this two-dimensional rotation matrix, they are this is a commutative operation. It is not non-commutative, and this is contradictory to what this task requiring. And so this is the high-level intuition why rope cannot handle this non-commutative task. And next, we want to use some other linear transformation to encode this swiping operation. And then we realize, okay, we can use this household matrix to encode this swipe operation. And so for household matrix, it is basically it performs elementary reflection. And here you can imagine here we have a mirror, and it map this this point to this point. Yeah, here we have a mirror, and we can map this this point to another point. If we choose this mirror properly, then it could be used for encoding this swiping operation, because we can change the position of these two vectors. So here, this is a very classical linear algebra result. We can take the difference of these two vectors, and we can use it to construct a household transform. And then if we use this household transform, it is a linear transformation. We use this transformation applied on different vectors, then we can swap these two vectors and leave the resulting other orthogonal vectors to be intact. And then now it should be very clear. This household matrix is very suited for encoding this swap operation. If we do the accumulated reflection, we can model the composition of swaps. And this is also basic knowledge from linear algebra. If you do this cumulative product of the matrix, and this matrix, each matrix is corresponding to a linear transformation. And by matrix product, you are doing the composition of different linear transformation. And here, if we do multiple cumulative product of the household matrix, then we can we can perform the composition of this swiping operation.
Songlin. So one question, Chen Wei asks, a language model trained with rope, can it handle swaps with chain of thought, even though rope itself cannot?
Yeah, train of thought can enhance the expressive power of the transformer. Yeah. So since this swap operation is definitely imagine when the train thought is large, the train thought is non-enough, and it could tackle down all those problems in the class of P. Yeah.
So chain of thought makes it Turing.
There are a lot of like theoretical results, and we know that this chain of thought can enhance and can significantly improve the expressive power at the cost of slower inference speed, because we need a very long train of thought to do this reasoning. Yeah, chain of thought can definitely help robot to learn these swapping operations.
Yeah. And this, what you're explaining right now, reminds me of also delta product, right? Where they allowed the eigenvalues of A to go also negative, and that also included swapping. So that also allowed like the state tracking to be enabled.
Yeah, it's very important to allow the negative eigenvalue for that matrix. Otherwise, it cannot do this reflection operation, and it cannot model this swapping. Okay. Here we have a generalized household transformation. So for the original household transformation, it only has this beta t equals to 2. So we have this elementary reflector. But in many cases, we want this beta t to be learnable. So if this beta t equals to 0, it basically this resulting transformation is an identity transformation. It means that the model can safely skip that position. It basically does nothing. And when this beta t is equals to 1, then this resulting transformation is a projection transformation. And here we have this picture to show this 3 operation. So when beta t equals to 0, and we do nothing, this vector is still here. And when this beta t equals to 1, and we do this projection to this -9, this -9 has a plane, and we project this black solid line into this plane. So we have this very short orange line. And when this beta t equals to 2, we do the reflection operation. Then you can imagine first we do this projection to here, and then we project it back to here. So this is a reflection operation. And this generalized household transformation has been used in some previous model like delta night and the delta product, as mentioned by Joe. So now we already know that the cumulative product of this householder matrix could help encode the composition of the swapping operation. And then in PaTH, we use this cumulative product as the positional encoding. So for rotary position encoding, you can imagine in the mid it is a bilinear encoding scheme, and in the middle we have a d by d bilinear weight matrix. This weight matrix is calculated based on the relative distance between I and J. And then we use this relative distance and multiply each channel's angle to obtain this resulting bilinear weight matrix. And for PaTH, here the bilinear weight matrix, this is a D by D matrix. And this D by D matrix was obtained by this cumulative product of this householder-like matrix. Yeah, the motivation is that we want to use this cumulative product to help model the swap operation. And then since this if you do swap operation on 5 elements, it is already a NC1 complete problem. Then if we use this cumulative product household matrix to use this mechanism for positional encoding, then PaTH is also NC1 complete because it can easily solve that composition of swipe problem. And in our paper, we have a proof that PaTH is NC1 complete under some mild condition. Okay, this is the PaTH. And then we evaluate this synthetic task, which I called multi-query. So 5. So we have 5 elements, and then first we have an action, like swipe the first position and the second position, and we do swipe, and then then we have a query asking the model, where is element 4? And the model must answer the position for that element. Yeah, and in the second stage, we also we do this permutation to do the swiping operation, and this state configuration has changed, and we ask the model, where is another element we can the model can generate. We construct this data set on the fly, so there's no predefined order. Yeah, and the motivation is that we want to test out if the model can track all of these 5 elements at the same time. So here we have a multi-query synthetic task. We keep asking the model where is different element, and the model must encode the position of each element in the model's hidden state.
And it's given like no explicit intermediate chain of thought. It has to just do it in each forward pass. Okay.
Yeah, here we do not allow for train of thought.
Yep.
Yeah, here we only concern the scenario we do not have train of thought.
Yep.
Yeah, the reason is that if the model can solve it without train of thought, then if we equip it with the train of thought technique, maybe it can first of all it can solve a more complicated task, and then to solve the same task, maybe it does not require that much train of thought token. So the total generation length becomes smaller, and it could translate to inference efficiency, and this is very important, right? Because currently we have this non-train of thought technique to help reasoning, but it's really expensive, and we really want to have some technique to mitigate this. Yeah.
Makes sense.
Yeah, because incorporating train of thought makes this study much harder. So here we do not have train of thought. We only focus on this very basic model to test out the power of this basic model. And now we use this sequence to do the autoregressive training. We use a language modeling like objective to do this decoder-only autoregressive training. And each S indicates a swipe operation. Yeah, we encode this as 5 swipe operation. There are up to 20 number of different swipe for 5 elements, and we have 20 tokens. And here we have query token. We have 5 query tokens because we have 5 elements. And finally, we have 5 answer token because we have up to 5 position. And then the total vocabulary size is like 30. Maybe we also have some beginning of sentence. Yeah. And we use this to construct a sequence, and we use autoregressive language modeling objective to train on this sequence. And the result is very obvious. So for rope, no matter how many epoch we are using for training, it cannot solve this problem because rope has very limited expressivity.
Yep.
For PaTH, it can easily learn to solve this problem without train of thought in very few epochs, indicating that, okay, this PaTH is very powerful in maintaining those very complicated states in its internal state. Yeah, which we have found is very cool. And then we have some other state tracking task. Here we have this flip-flop language modeling, and it is also a sequence of action. It has write, read, and ignore. So the model must record the last return bit at that read token. This is also a simple task, and we can see PaTH can easily solve this task. And for other positional encoding, they have very high error percentage when evaluation out of distribution tokens. And in our paper, we show PaTH can probably solve this FFLM task. Yeah, we have a theory to construct that proof. We also have another synthetic task. This is another one. It's very similar to the composition of swiping task before. This is called the A5 word problem task. It was from the illusion of state in state space model paper. And we also can see that PaTH, when we increase the sequence length, and for other positional encoder like rope and forks, stick breaking, they need linear amount of layer to solve this task. But for PaTH, it only need a logarithmic number of layers to solve this with respect to the input sequence length. So we can see here as the increase of the input and the number of layers required to solve this task for PaTH will be significantly lower than other model when we keep increasing the number of the sequence length.
Yeah, and for context, A5 here is the alternating group.
Yeah.
Yeah.
We have some group. Yeah.
Yeah.
This problem is very similar to that composition of swipe.
Yeah.
I found that composition of swipe problem is more intuitive to understand.
Yeah.
Yeah. Okay, firstly, we have some synthetic benchmark. Then, if we want to use PaTH in practice, here I give several recommendations. So the first one is the distillation pipeline. There are a lot of models trained with rope, and we want to start with these checkpoints, and we want to change these attention layers from rope to PaTH. And then we have this two stage. In the first stage, we take the golden input and output from the teacher rope model, and for the student model, the rope is replaced by PaTH for all of the layer. And we have the teacher model and the student model. The teacher model is the original pre-trained model, and the student model is the student model's weight is initialized using teacher's weight, and then we have some misalignment, and we have a two stage to reduce this misalignment. In the first stage, for each layer, it has the golden input and the output from the teacher, and we calculate the L2 distance loss to want to minimize that mean square error. And in the second stage, this is end-to-end loss. We just minimize the output logic. KL divergence is like the vocabulary output distribution. We want to minimize that KL divergence. This is also known as knowledge distillation.
Wait, so Songlin, question. So intuitively, since PaTH allows you to model reflections, right? And rope doesn't. Rope's all about rotations. And now we also know mathematically, correct me if I'm wrong, but 2 rotations can model 1 reflection, right?
Actually, it is in the reverse direction. 2 reflections.
Oh, 2 reflections
can model 1 rotation.
Okay, I see. So, for the same number, if we're just considering the attention between 2 tokens, now the rope style is going to look at their relative position, but PaTH can potentially I'm trying to think geometrically how they can be converted into some equivalence when you're doing this distillation.
Yeah. Yeah, this is a good question. So if we use two household matrices
Yeah.
for a single transition, this is actually a ongoing work. I'm trying to use
Okay.
two household matrices to
Yeah.
for a single transition.
Yeah.
Yeah, if we use two household matrices for one transition, this is very trivial, right? Because two reflection matrices could encode one rotation matrix.
Yeah.
But here we just don't care that much. We just
Okay.
use this function to minimize the loss,
Okay,
and
okay.
we are okay with it.
I see. Okay, got
We
it.
don't want to do some closed form reconstruction of rope.
Yeah.
We can use some indirect way to encourage them to be as close as possible.
Yep. Okay, makes sense.
And here is a preliminary result. And the teacher model, I take the Quern 2.5 7B instruction model. And I only use 100 million token for stage 1 and 3 billion token for stage 2, comparing to pre-train, which has trillions of tokens. Here I only use a very small amount of token, and then I can recover most of the performance. And for some tasks, it is even better. And I also have a setup called continue pre-training. We do not have that resource to do pre-training from scratch. Then maybe we can use some intermediate checkpoint. For example, here we have this small checkpoint from Hugging Face. They have a lot of checkpoints, and they are using some training schedule that in the final state they feed a lot of high quality data to do this layering, and then we can take this pre-decay checkpoint and we can use high quality data to do this continuous pre-train. And here we can easily see the gap because here it is a fair comparison. We have the same training data, we have the same training novel training token, and they should be totally comparable. For the first one, it is not that easy to show the difference, but for this one, we can have a controlled experiment, and it is very easy for us to do this architectural research based on this continuous retraining, and we can see PaTH clearly outperform rope in coding and math benchmark like GSMAK, human-aware, and then BPP. I used some very dumb data mixture. I just used 1/3 of the code corpus and 1/3 of the mask data and 1/3 of the text data. And I only use 12B token for the continuous pre-training. And we already can see a lot of very good positive signal for it, especially on coding task. In coding task, you can imagine it's also very relevant to state tracking. And like you have some variable X, and during this later on, this variable could be reassigned to another value, which happens a lot. Yeah, and in coding definitely require the model to have some certain state tracking ability. And in the second experiment, I purely do the continuous pre-training on the mass data, and we can see this gap becomes larger, and clearly PaTH is better at this mathematical and coding task due to this better expressivity power, especially in this state tracking task. And later I'll show how can we train this PaTH attention at scale. And so here we have a recap of the PaTH attention's encoding scheme. We have this cumulative product of this household like matrix to serve as the bilinear weight matrix, and we use this bilinear attention logic computation for encoding this And here we have this beta, because we are using the generalized household transform. This beta can be relaxed to 0 to 2. And the WT is L2 normalized. It's also a nullable vector. We basically, it's very similar to QK. We have another linear projection from the input data to calculate this WT. And we need to use this L2 normalization to make sure this transition matrix, the largest eigenvalues, absolute value is smaller than 1. Otherwise, it have some stability issue because here we have the cumulative product. And if the transition matrix, the spectral noise is not bounded, and when you do this cumulative product, it will become larger and larger. In order to train in a hardware efficient manner, we must be doing some block-wise algorithm like flash attention, right? And here we have two positions, I and J, and we divide the sequence into multiple blocks. Each block has the same size, and then we can, so this key must be located in one block and this query must be located in another block. Then there could be some block in the middle. And we divide this calculation into several parts. The first part is that for each key, it must be doing this cumulative product of this household within that block. Yeah, so for each key within that block, we must be apply this household matrix to the very final position for later use. And there should have some dynamic programming to reuse lot of calculation. Yeah, we map that to a shared point. This is very important, and this is also very hardware aligned because we want.
What do you mean you map it to a shared point?
For each token in that block, for example, we just want to do the cumulative household transform up to the last position. Yeah. So each key are transferred to that position. Yeah.
Okay.
Yeah. So for different positions, they apply different number of household transform.
I see.
Yeah. We just want to make sure that they are all transferred to that point. Yeah. So they have a shared point. And then we have some cumulative product of this household matrix in the middle. Yeah, because these are already blockwise computation. And then we can use this. There is a very classical algorithm called the UT transform. It was used for calculating the cumulative product of household matrix in a very efficient manner. And here we can write it as a matrix product and this matrix inverse. You don't need to be freaked out by this matrix inverse term because normally the block size is not that large. The block size is like 64. And even this takes cubic time, we are doing it locally within that block. And since the block size is small and this cubic complexity is not a problem, we are not doing this cubic complexity on the sequence length, right? It's only in the block size, so this is also cheap. And this could be, this is a loyal triangular matrix. Yes, and we can calculate this using the forward substitution. And then for the rest, we can use matrix multiplication to calculate this cumulative product.
Yep.
And similarly for query, for keys, we want to transfer it to some future position. But for queries, we want to do this cumulative transformation to a shared point again. But that position is a forehand of all the query token. Because for query, we want to do this application in the reverse direction, right? And here is very similar. And in the paper, I do some math. I don't want to show it here because it's very tedious. I just show the results. I did a lot of derivation in the paper. So basically, for each for this one, we call the transferred query. And when we pack them, we use this to pack them. So for each position, it's already a transferred query. to make sure it is distinguished from the original query. And we have this left arrow to indicate the household transformation direction. For query, we want to do it from right to left, and for keys, we want to do it from left to right. So this head indicates the direction.
Yeah.
And here we have some matrix multiplication operation to achieve this transform. Yeah, I won't explain it right now because it's tedious. You'd better, if you are interested in it, you'd better check out the paper. But my main point is that a lot of calculation, almost all the calculation, can be written in matrix multiplication. And we all know that matrix multiplication is very fast on modern hardwares like GPUs. We can leverage the tensor cores and to do this fast memo. And the most headache one is this matrix inverse, but the block size is small and we can totally accept it. It's actually it's very fast in practice. Yeah, then this cubic matrix inverse is not a problem at all. We can do this matrix inverse for different block independently in parallel.
Yeah.
We can average the GPU parallelism to calculate the matrix inverse for each block. Yeah. Yeah, for this slide, I want to convince you, okay, this algorithm is very hardware aligned and we can, it is possible to train it very fast on hardwares. And then we can adapt the flash attention algorithm for computing this path attention. So I colored the main change in pink. And so for this is like in the style of flash attention 2. So we have this query block loaded into the shell memory, and we do a scan of over these key and value blocks from left to right. But here, first, I must change the order of this scan because there's some order requirement. For rope, it uses absolute position encoding to encode this relative position. So it doesn't matter at all which direction you use for this scan. But for path, because it's used relative position, then you must do this encoding from the nearby block to faraway block. Then we must change the order of this scan from right to left. And for each one, I have this transferred query and this transferred key. We load this into the shell memory. And in addition, we have this block level household cumulative product. And we calculate this attention object as such. And very similar to flash attention, we need to update some online softmax statistics and accumulate the output. This is exactly the same as the flash attention. So I won't explain it. I only highlight the difference. And the key difference is that after each block calculation, I need to update the query and to incorporate that cumulative household transform. Yeah. Then during the scan, this cumulative household transform was implicitly encoded in this query. Yeah, we use some associativity property of matrix multiplication to achieve it. So we can keep applying this cumulative household matrix on this query block. Yeah. And you can see this is also not that hard, right? And we can use it for very hardware efficient training.
Have you like benchmarked the
Yeah, I have some benchmark number,
Okay.
but Triton is not that easy to compare with like Flash Attention 3. I don't think that benchmarking number is so meaningful. Yeah, in workload time, it's like currently it's like for the kernel wise, it's like twice slower than Flash Attention's kernel.
Yeah.
But I'd expect some further speed up using some more advanced, like if we rewrite it in CUDA DSL, that will be much faster. Yeah, I found that benchmarking number is not that informative. Yeah, just ignore it. I deliberately ignore it. And I only want to convince you this blockwise algorithm is hardware aligned and we can only use some very minimal modification on the flash attention algorithm to derive our path attentions algorithm. And for the inference, we can reduce path attention inference to some mass attention inference actually. So for each time step, we have the incoming this householder matrix, and then we use this householder matrix to apply it on all the historical keys. And in this sense, you can imagine we are using future information to keep refine the key K cache iteratively. So effectively, each future step we do this refinement, and then in total we can have this cumulative product of this household matrix. And here we are doing some rank one update, rank one refinement. We take most of this identity part, so we maintain this the old key, and we have this rank one update to accommodate the new information. And this is also very interesting. You can imagine this path attention. There is a mechanism to dynamically change the key cache. Yeah, so previously the KV cache doesn't change at all. But if we can have some hardware efficient mechanism to dynamically address this key cache, this would be very interesting, right?
Yeah.
So here we have this key cache adjustment, and then there's a open question: can we also apply this operation on the value? So we can do this rank one refinement on KV cache at the same time. And then once we do this transformation, then you must know each historical key are already transformed to the latest position. Yeah, then we just need to use this query to do this vanilla dot product. And in this stage, we can reduce it to flash attentions decoding. We can call arbitrary accelerated attention decoding scheme to do this path attention decoding, like flash decoding, stuff like that. We can reuse this kernel. We can definitely rewrite it in VRM to leverage this page attention thing. Yeah, and it's also totally possible to fuse this rank one update and this flash decoding thing into one single kernel. And you can see the major I/O course is the loading of a single W vector. It's not the entire W vector. We do not need to cache these W vectors for history. We do not have the corresponding W cache because we are using this W cache to directly transfer the key cache. Then this W could be discarded. We do not need to save it. And this is also very important. And in the decoding, we can like loading the query, we can load this W. This is like a one-time course. Yeah, there's no very large no W cache to load, and this loading is very fast. And the only additional overhead, I think, is like we need to write this updated key back to the HBM. But I think because this could be overlapped to some extent, we can load this key block to share memory, and we do this 09 rank one update, and we can write it back, and we can and then we can also load the next key block. And I think there's a lot of pipelining thing to do
It's
here.
interesting how this would, because there's a lot of work that people do for KV cache optimization for efficiency, right? And the fact that you're saying now maybe we should actually change the KV cache as we're iterating, like in decoding from the transformer. I wonder, like, would this actually cause us to now change how we're doing a lot of the KV cache optimization, which has this assumption of a fixed KV cache?
I think this path attention doesn't change the nature of fixed KV cache. We are still doing a lot of we still need to store the entire KV cache. Here we are not focusing on efficiency. We are focusing on more like the expressivity, and I want to convince you, okay, this could be implemented in an efficient manner. Yeah, it's definitely not gonna be faster than than facial attention. But I think like maybe if you have a more expressive mechanism here, you do not need that larger dimension.
You
for
might
the
not
for,
even need as many decoding steps either.
yeah,
Yeah.
you don't need that large dimension for this KV cache. Maybe you can your KV cache could be compressed into a low dimension, or maybe if some key cache are already this is like some kind of decay. If this key cache already decay to 0, you can discard it and you can have some placeholder to know. Okay,
That's true, because the spectral since W is normalized, right?
Yeah.
And the spectral norm of this should be bounded between like
Smaller than 1.
right?
Yeah, and we are doing this
Okay.
generalized household thing.
Yeah.
Yeah, we are not doing this norm preserving operation. Then maybe not enough. We can, if this approach to 0, we can just discard it.
Is there, because we're always multiplying by value less than 1, is there any vanishing gradients issue?
I think the model can decide, right? The model can dynamically if the model really want to have attend to very long distance, you know,
make
this
this one.
beta t is a dynamic, it's data
Yeah,
dependent,
that's right. Yeah.
and we can make it to be 2. Yeah, this is very similar to like in member in gating linear attention. We have the gating mechanism. If the model want to attend to very far away history, you can let the decaying value to be 0, basically no decay at all. The model can learn it. We can trust the model's learnability. Yeah, and for some many other head, maybe you just use for modeling the local information, and this could be decay very fast, and we can safely prune those key cache, and this is one possible way to improve the efficiency. Yeah, good question.
Fox.
Yeah, I'm not sure if we are running out of time. Do we have time limit actually?
Yeah, no, there's no
No, you can just keep.
You
okay, I can keep chatting.
This is fantastic.
Yeah.
Okay.
By the way, I before you go on to this, I'm actually very curious, like, if you guys have looked at all into, for example, like what the model chooses for W, like, and what I mean by this is like, if you observe some kind of like similar structure to what rope is doing, which is basically just like fixed rotations, or if it's like very hard to discern what's going on with its choice of like a reflection point. I'm just curious. I don't know, because like in theory it can generally express rope transformations, but I'm assuming it probably does not. And I'm curious like how close it is to a rope transformation, or if it just is something completely different.
Yeah, this is also an interesting question, but I will investigate. I don't know what this network then. I just have this mechanism at the ladder level then itself.
The other thing is, like, do you think that they're because I think that from what I can understand, like there's a big jump between these like fixed positional encoding schemes and then this kind of method. And there probably is another jump from this kind of method to just allowing basically freely learning what the transformation, this like whatever the positional encoding is. Like, is there something particularly special about doing or using the householder matrix or like reflections in general? Or like, I guess I ask this because like, what's stopping you from just allowing the model to learn an arbitrary matrix to do these intermediate kind of transformations?
I think this is mostly for efficiency consideration. Yeah, if you have arbitrary matrix and you do those iterative matrix product, you know, if you have 2 arbitrary matrices d by d and you do the matrix product, it takes d cubic time. Yeah, it is not affordable. For household matrix, it is a structured matrix, and it has very nice property. We can use the aforementioned UT transform for efficient calculation. And we can do for two d by d household matrices, their product could be achieved in d square time instead of d cubic time. So this is the main motivation for choosing household matrix. Yeah, and later, out of our surprise, like there's other work showing that this household matrix could improve state tracking. I think like last year, last year, there's a paper called allowing negative eigenvalue can unlock the state tracking capacities. They propose this generalized household matrix, and before we cook with the data net, we do not allow for negative eigenvalue. And then I started looking into this negative eigenvalue thing, and I think this is very intuitive, at least geometrically speaking. It allows for this reflection operation, and for many tasks of interest, we do need this reflection operation. You can imagine that some discrete operation trying to flip-flop that memory bit, and for rotary position encoding, because the rotation is continuous, and it doesn't allow you to do a abrupt distort of the memory content, but this reflection operation could allow you to such abrupt operation.
I see. I see.
Okay. Maybe I also have some minutes to talk about PaTH. It is another variant. Before talking about PaTH, I'll first talk about the forgetting transformers. Forgetting transformers is very. You can also imagine forgetting transformers as a positional encoding. I think everyone should heard of the term called alibi, and it is a positional encoding scheme. And forgetting transformers, you can imagine it as a data-dependent version of alibi. Here is the attention notches encoding, and it has the cumulative product of this scalar value. You can imagine that forget gate, and it has this for encoding the attention notch. Since this forget gate can help the model to quickly to decide what kind of memory content to forget. And also in their paper, they show this dynamic forget gate is beneficial for length extrapolation. And we can combine these two mechanisms as a whole. So by PaTH, here we have the path bilinear attention notch encoding scheme. And then we can have this cumulative product of this forget gate. Usually this forget gate is parameterized under the exponential function, and then you can here we also have an exponential function. We can put this inside of this exponential function bracket, and it becomes a bias term then. So in this sense, I think alibi or forgetting transformers, they can be imagined as additive positional encoding. They can be used as a bias term for this attention object. And for rope and for path, they are multiplicative attention object encoding scheme, because we have this bilinear weight matrix here for this attention scoring. So combining these forks and the PaTH, we are combining the multiplicative positional encoding and the additive positional encoding. And there's also a very interesting connection to the linear attention literature. So for NOPE, we have the linear attention counterpart. It's just like we have this one linear attention. We do not have the softmax operator. And then for frogs, the corresponding linear attention model is like Mamba2. It is a very famous model. If we remove this exponential function, and then this forgetting transformers becomes Mamba2. For PaTH, again, for example, in this one, we do not we ignore this part first and ignore this exponential function, and for the remaining one, it is just a data net. So for PaTH, it could be imagined as data net with the softmax operation. And for PaTH Fox, you can imagine it as a gated data net with the softmax operation. And I think these two mechanisms has complementary strengths. So for in the linear attention literature, since the memory capacity is highly bounded, then a lot of researchers just trying to find some more expressive attention logic encoding scheme like data9 to encode the attention logic. And in this sense, as we show, this encoding scheme even allows for theoretical expressivity separation between this NC1 and TC0 separation. But even though the expressive power is higher, it also has a very significant drawback. That is the memory capacity. For nonlinear arms, they have really strong expressive power, like ASTMs, like a gated recurrent unit.
Yeah.
They are nonlinear arms. They have a very strong expressive power. They can model a lot of things that transformers cannot model. Yeah, in terms of expressive power, they are better.
Yeah.
But the key bottleneck is first one is training. Second one is the limited recurrent hidden state size. They only have a fixed amount of hidden state size.
Yeah.
So they have a very small memory capacity, which is definitely problematic. And the softmax attention, you can imagine from the perspective of kernel method, a softmax attention could map this into a infinite dimension RNN, and then these RNNs, you can even imagine a softmax attention as RNN with an infinite hidden dimension. And in this sense, we can argue this softmax operator is mainly used for improving the memory capacity. Yeah, we have, and this point of view has also had a lot of connection with the whole field neural network literature. They have a lot. They are trying to use different activation function, and in the end, they end up with the modern whole field level. They use this exponential function for better separation, and once you have better separation, you can store more contents in that energy network.
And just for the audience, when Songlin said the infinite softmax can be expressed in infinite dimension, that's when you do a Taylor expansion.
Yeah, if you do Taylor expansion, you can obtain the infinite hidden dimension. If you do this truncated Taylor expansion, for example, if you just take the first two order, the first order, the second order, there are several, for example, tensor power, linear attention. They use this truncated Taylor expansion, and also base linear attention from Stanford, by my friend Simran. And they use the truncated Taylor expansion to do this linear attention. There are a lot of connections between linear attention and softmax attention. Yeah, they are connected by this kernel function. Yeah, and then since we already have this model like DataNet with better expressivity, and also it has a very good scalability property comparing to STMs and gated recurrent unit. And the motivation of this project is actually, why can't I just put this softmax operator back? Then And then this expressive model also have a very large memory capacity. They combines the best of two worlds. Yeah, this past project is actually motivated by forgetting transformer. Yeah, last year I saw this forgetting transformers in clear open review, and I start thinking, why can't I just combine the softmax operator and the delta rule into a single model? And then I result in this path model.
So this is kind of like softmax plus actually like delta product.
Yeah.
Right.
But here it's mostly delta net because I only have one householder matrix as the transition matrix.
Oh yeah, and delta product.
They have multiple householder matrix
Yeah.
for each transition.
Yeah, there's another one, unlocking the state. Something.
That's
okay.
that one.
Yeah,
I use the lective eigenvalue because I want to emphasize more on the state tracking side, because I think this state tracking is overlooked. It has a lot of correlation with this like reasoning and coding and mathematical property. Yeah. Yeah, like before, this NC1 model can do like a Bourne function evaluation very quickly. Then this I believe this kind of model can better handle this coding and the math task. And previously, I also have some continuous pre-training result to empirically verify this. And for GetGate, I think it's mostly very useful for Nancy extrapolation. And in the final, I have some pre-training from scratch experiment. Previously, we have some distillation experiment, we have some continuous pre-training experiment, and now we have this pre-training from scratch. And we can see this is very common benchmark, the common sense reasoning, language modeling benchmark. We can see this PaTH and PaTH-Fox outperform both rope and Fox, showing that this delta rule, this household community model is definitely doing some good thing here. And for Nancy extrapolation, I found this dash 9 is rope. We all know that the training sequence size is 4K. When we go beyond 4K, the rope has much higher probability. This is very as expected. And for Fox, it's very interesting because for Fox, it usually it can extrapolate to some extent, and then the probability rise up and until an intermediate point, and then not start going up. I found this interesting. I think this is probably because for forgetting transformers, it just forget the historical information. It acts like a soft version of a sliding window. Yeah, for sliding window, you can do extrapolation, but you cannot have this long-term dependency. When you evaluate it on longer sequence, this probability can go up. Yeah, because it cannot handle all those information. And for pass without the forget gate, like for this task, it can also be exploding. Yeah, and but its behavior is much better than rope. And so in terms of this pass attention can do better extrapolation. Yeah. But we are not expecting it. We don't expect that we do not need retrain on longer sequence data to recover this property. In the end, we need to train on longer sequence to do this next extension to have true non-contestability. But I think this next extrapolation experiment has some positive signal, especially for PaTH plus Fox. It does this extrapolation very well. And the probability doesn't have this this strange blow up in the middle, and the probability curve is like very flat. Here we have some benchmark number because this is very small model, and we found PaTH and PaTH-Fox performs very well on this non-context benchmark. And it's also worth noting that for this variable tracking task in the ruler, this is a task specifically for state tracking. And we can see PaTH and PaTH-Fox has significant advantage in this subcategory than Fox and Rob.
Nice.
And thank you for listening.
All right. Thank you, Songlin. We do not. Yeah, that was a great talk. Very dense. I'll probably have to rewatch it later. We do not have any more questions, but Alex, do you have any questions?
I'll leave that for offline. Just so, yeah. If anyone has any questions, you have to ask them now. I guess we have been running for some time now, so
Yeah,
we could just keep it here. But
I
thank
guess
you all.
maybe not, because we haven't had any questions for some time.
Yeah.
Yeah.
Thank you all for coming.
Yeah.
This was a great talk. I think tomorrow is the last day. It will be basically completely focused on GPU programming, which I guess maybe most of you are more familiar with.
Yeah.
Tomorrow also will be longer than any of the days because there will be 2 speakers.
Yes.
So I think we haven't decided yet if we're going to split it into 2 talks, but it might just be one giant stream, which we'll see. But yeah. All right. We'll see you guys tomorrow.
All right.
See you.
Thank you, Songlin.
Yeah, thank you.
Okay.